And the first reason, I think, is that it's because the developers of the commercial software systems aren't doing it, or at least not doing it enough. And I think it's pretty clear that the kind of bugs found, for example, in the fuzzing papers or in Charlie Miller's talk wouldn't have been there in the software if the developers of Adobe Acrobat or of the Unix utilities had had a reasonably aggressive random testing program. And remember that some of those bugs Charlie Miller was talking about were security vulnerabilities. These are things that they really don't want in their software. And so what I'd argue, that software development efforts that don't make proper use of random testing are flawed. And the reason that these efforts are flawed is because modern software systems are so large and so complicated that test cases produced by non-random processes are simply unlikely to find the kind of bugs that are lurking in these software systems. And so what that leaves us with is a question, well, what should they have done? How's random testing supposed to work? And so let me give some ideas about that. What I'm going to do here is show sort of a rough software development timeline with the releasing software over here and early development stages over here. And so what we've looked at mainly so far in this course is random unit testing. So we're developing these software units, and what we're trying to do is make sure that they are robust enough that when we start composing them together later, that they'll be a solid foundation. So we've looked at several cases of, for example, with the queue, bounded queue here, we looked at fuzzing the interfaces that it provides. We also looked at an example of random fault injection, and that was for the read all function. And if you remember, that was the function that was supposed to cope with the fact that the Unix read system call can display partial success. So there we were doing fault injection, so we were fuzzing the interface used by the read all call, not the interface that it provides. And so like I say, what we want to do is ensure, as we're developing the modules, that we're creating robust pieces of software whose interfaces we understand and that are going to be a solid foundation for future work. So as we start developing more elaborate software stacks, it's going to be the case that some of our random testers become useless. So for example, if we have a queue instantiated here that's used by some more sophisticated piece of software, we no longer are interested in the ability to randomly test the interface provided by the queue because it's simply being used by the rest of the software. On the other hand, other kinds of random testers, such as those that come in at the top level and those that perform system-level fault injection, are absolutely still useful. And in fact, fault injection of things like erroneous responses to system calls are really important things to test larger pieces of software with, because typically those kind of errors can result in failures propagating all the way through our software stack, and we'd really like to understand how our system responds to that sort of thing. As we approach something that's more of a complete product, our focus should be on external interfaces provided. So this is going to be things like file I/O and the graphical user interface. And so if you recall, those fuzzing papers were fuzzing exactly these sorts of things. They were delivering random bits through the file interfaces, and they were delivering random GUI events to applications, and knocking over a pretty large proportion of applications that they tested.